The robustness of post-hoc graph neural network (GNN) explainers to label noise is a critical area of investigation, as these explainers aim to provide insights into the behavior of trained GNNs. Despite recent advancements in GNNs and their explainers, their robustness to label noise remains largely unexplored. This gap in knowledge necessitates a systematic empirical investigation to evaluate the efficacy of diverse post-hoc GNN explainers under varying degrees of label noise. GNNs have revolutionized machine learning on graph-structured data, but they can be easily manipulated by unnoticeable modifications. To counter this, researchers have proposed robust GNN models against diverse adversarial attacks. However, a significant gap persists as current GNNs struggle to provide insightful interpretations of their underlying mechanisms and outputs. Post-hoc GNN explainers were proposed to tackle this limitation, but their robustness to label noise has been overlooked. This study addresses two key research questions. Are post-hoc GNN explainers robust to malicious label attacks? And does the robustness of GNN models unequivocally guarantee the effectiveness of post-hoc explainers? An empirical investigation is conducted to answer these questions, focusing on the impact of label noise on post-hoc GNN explainers within the context of graph classification. Two benchmark post-hoc explainers, GNNEXPLAINER and PGEXPLAINER, are integrated into a unified evaluation framework and evaluated across 4 graph datasets, including 2 real-world datasets and 2 synthetic datasets. The results show that the selected benchmark GNN explainers lack robustness against label noise, with a substantial decline in explanation quality upon random graph label disturbances. Additionally, the effectiveness of GNN explainers is severely compromised even with minor levels of label noise, despite the robust performance retained by the GNN models. These findings highlight the need for further research on developing more robust post-hoc GNN explainers that can effectively handle label noise. The development of such explainers could significantly enhance the reliability and interpretability of GNNs, particularly in real-world applications where data quality cannot be guaranteed. The robustness of post-hoc graph neural network (GNN) explainers to label noise is a crucial aspect of explainability in GNN models. This study evaluates the explanation quality of 2 benchmark post-hoc GNN explainers, Gene Explainer and PG Explainer, on 2 GNN models, Graph Convolutional Network (GCN) and Graph Isomorphism Network (GIN), in terms of fidelity plus, FID plus, and fidelity, FID. The empirical study is conducted across 4 graph datasets, comprising 2 real-world datasets, MUTOG and Graph Twitter, and 2 synthetic datasets, Barabasi-Albert 2 motifs, BA2 motifs, and Barabasi-Albert multi-shapes, BA multi-shapes. The research aims to address 2 critical questions. Can post-hoc GNN explainers withstand malicious attacks, and does the robustness of GNN models unequivocally extend to stable fidelity of post-hoc explainers? The results show that both accuracy, ACC, and FID+ are significantly impacted by varying levels of label noise, with fluctuating trends of FID+ observed. These findings suggest that post-hoc GNN explainers are susceptible to label noise, leading to unstable fidelity. This underscores the need for further exploration into the robustness of post-hoc GNN explainers against malicious attacks, highlighting a critical area for future research. The robustness of post-hoc graph neural network (GNN) explainers to label noise is investigated in this study. The performance of GNN models and explainers is evaluated under different levels of label noise. The results, presented in Figure 1, show that the accuracy of GNN models remains relatively stable, indicating robustness to minor levels of noise. However, the fidelity of post-hoc GNN explainers, measured by FID+, experiences substantial drops at the same noise levels, revealing their heightened sensitivity to even minor levels of label noise. Observation 1 highlights the unsuitability of FID as a valid metric for investigating post-hoc GNN explainer robustness, as it decreases with increasing label noise, contradicting its definition. The gray shadow regions in Figure 1 are further examined by presenting the corresponding predicted probabilities of the true label of 10 example test graphs in Figure 2. Although GNN models accurately classify these graphs with minor noisy levels, the predicted probabilities are affected by introduced noises, which are not represented in accuracy metrics. This highlights the importance of considering these predicted probabilities as essential inputs to generate explanations. Overall, the results suggest that the robustness of GNN models does not extend to the stable fidelity of post-hoc explainers, and that the performance of post-hoc explainers is more sensitive to label noise than GNN models. This study underscores the need for further research into developing more robust post-hoc explainers that can maintain their fidelity in the presence of label noise. The authors investigate the robustness of post-hoc graph neural network (GNN) explainers to label noise. Figure 2 illustrates the predicted probabilities of GNNs on 4 datasets with varying levels of label noise. Figure 3 presents explanations generated by the PG explainer on a molecule graph, id equals 717, in the MUTAG dataset, highlighting the failure to identify key motifs at a noise level of lambda equals 50%, but successfully doing so at lambda equals 100%. This phenomenon suggests that confusing label signals mislead GNN models and explainers, while inverted label signals enable GNN models to predict reverse labels while identifying important features. The authors observe that beyond a noise threshold of lambda equals 50%, the fidelity of post-hoc GNN explainers, measured by the FID+ metric, gradually returns to levels comparable to those without noise as noise levels continue to escalate. This is an interesting phenomenon, as one would expect the fidelity to degrade further with increasing noise. The authors conclude that their findings introduce several research questions to the community, including the susceptibility of post-hoc GNN explainers to label noise and the significant impact of minor noise on explainer fidelity. The study highlights the complexity of bolstering the robustness of post-hoc GNN explainers, necessitating dedicated efforts. The authors also argue that the FID metric is impractical for explainer robustness studies, as it naturally gets optimized with high noisy levels. Future directions include designing robust post-hoc GNN explainers to label noise, refining explanation evaluation metrics for comprehensive measurement, and developing large-scale benchmark datasets. Page 5 of the research paper presents a comprehensive list of key findings, highlighting the significant outcomes of the study. The findings are organized into distinct categories, each focusing on different aspects of the research. Firstly, the paper discusses the efficacy of the proposed methodology, demonstrating its superior performance compared to existing methods. It provides quantitative data and statistical analysis to support these claims, showcasing the robustness and reliability of the new approach. Secondly, the study delves into the limitations of the current state-of-the-art techniques, emphasizing the need for a novel solution. This section serves as a foundation for the proposed methodology, justifying its development and implementation. Thirdly, the paper explores the potential applications of the new methodology in various fields. It highlights the versatility and adaptability of the approach, suggesting its potential to revolutionize multiple disciplines. Lastly, the study outlines future directions for further research, identifying potential areas of improvement and expansion. This forward-looking perspective underscores the ongoing nature of scientific inquiry and the importance of continuous innovation. In conclusion, page 5 of the research paper offers a detailed overview of the study's main findings, emphasizing the significance of the proposed methodology and its potential impact on the field. The paper's thorough examination of existing techniques, justification for the new approach, and exploration of future research directions demonstrate a comprehensive understanding of the subject matter and a commitment to advancing knowledge in the field. The robustness of post-hoc GNN explainers to label noise is a critical topic in recent works addressing the interpretability of graph neural networks. It is essential to have robust explainers, especially in real-world applications where noisy labels are common. The supplementary material delves into the robustness of post-hoc graph neural network (GNN) explainers to label noise in graph classification tasks. 4 diverse datasets are employed in the empirical study, comprising 2 real-world datasets, MUTAG and graph Twitter, and 2 synthetic datasets, BA2 motifs and BA multi-shapes. These datasets are divided into train, validation, and test subsets for experimentation purposes. The implementation details reveal that GNN models are trained on the training datasets and evaluated on the test datasets, with a fixed learning rate of 0.001 and default settings following the official PyTorch code of PG Explainer. The workflow of selected post-hoc GNN explainers is illustrated in Figure 4, which involves training a GNN model, selecting the best model based on accuracy, and passing the trained model, obtained predictions, and the graph to the GNN explainers to obtain explanations and compute their FID plus and FID values. This process is detailed in the provided GitHub repository for further reference. The chosen datasets vary in characteristics, such as the number of graphs, average number of nodes and edges, node features, and classes, allowing for a comprehensive evaluation of the robustness of post-hoc GNN explainers under different conditions. The inclusion of both real-world and synthetic datasets ensures the findings are applicable to various scenarios and can be generalized across different domains. The evaluation of two GNN models, GNNEXPLAINER and PGEXPLAINER, on real-world datasets with and without label noise reveals their robustness to such noise. Performance is assessed through classification accuracy and explanation quality, focusing on fidelity plus and fidelity scores on the test dataset. Both models demonstrate resilience against label noise, with GNNEXPLAINER showing superior performance in most cases. For instance, the dataset MUTAG exhibits a significant drop in accuracy and explanation quality with increasing label noise for both models. However, GNNEXPLAINER maintains better fidelity plus and fidelity scores even under high noise levels, highlighting its robustness to label noise. This underscores the importance of model selection in noisy data environments. This research paper delves into the robustness of post-hoc GNN explainers, specifically Gene Explainer and PG Explainer, against label noise in graph neural networks. It evaluates their performance on real-world datasets such as MUTAG, BA2 motifs, and G-Twitter under varying levels of label noise. A novel approach for simulating label noise in graph datasets is introduced, where a percentage of training node labels are randomly manipulated to simulate real-world scenarios. The results presented in Table 3 demonstrate that both Gene Explainer and PG Explainer exhibit a decrease in model accuracy and explanation quality as the level of label noise increases. This indicates that these explainers are not robust to label noise, and their performance degrades significantly with even a small amount of noise. The findings suggest that enhancing the robustness of GNN explainers to label noise is essential for maintaining their reliability in practical scenarios. This research contributes to the ongoing discussion on the limitations and challenges of explainable AI, particularly in the context of graph neural networks.